Would you like to know how to do proof trees for intuitionistic logic? If you would, stick around, I'm going to talk you through it. Hello everyone, welcome to the Attic. My name's Mark Jago. I'm a professor of philosophy in the UK. In this video, I'm going to be walking you through how we do proof trees for intuitionistic logic. And kind of a bit of a warning up front, these do get a little bit tricky. So we're going to walk through the rules fairly slowly, and I'm going to try and explain why they work the way they do. Okay, so if that sounds good to you, do me a favor before we get going, subscribe to the channel, give this video a thumbs up, and hit that bell icon to get notifications. I'm going to start off with a little bit of a health warning. Proof trees for intuitionistic logic are pretty complicated compared to propositional logic, first order logic. They're even a bit more tricky than proof trees for modal logic. I'm going to explain why that is first up, and then I'm going to get on to what the rules are and how we use them. There's timestamps down below, so if you just want to skip on to what the rules are, feel free to do that. But let me just talk you through a little bit why they have to be so complicated. So if we think about how proof trees work in propositional logic, if we're trying to work out whether some premises X entail or prove some conclusion A, what we're going to do is we're going to write down the premises, the negation of the conclusion, do some stuff, and try and get the branch to close. If we can do that, we're basically saying something's gone wrong from the assumption of not A. Okay, so given the premises and also not A, if something goes wrong, then we can infer that, given the premises, A must follow. Okay, if it can't be not A, it must be A. So we're basically doing reductio, right? We're going from premises, assuming not A as well, something goes wrong, so we infer A. And then we say A follows just from those premises. But reductio isn't valid in intuitionistic logic. So does that mean that proof trees can't be used intuitionistically? Here's another way to think about it. We're assuming not A and getting a problem, which is kind of telling us not A, but we don't just infer not A as following from the premises, we infer A as following from the premises, right? We're trying to get A as our conclusion. So it's kind of like we're going from not A to A, but that's banned in intuitionistic logic. We can't do double negation elimination intuitionistically. So again, are we just not going to be able to use this style of proof trees for intuitionistic logic? Now it turns out we can, otherwise I wouldn't be doing this video, right? But we have to kind of cheat a little bit. One way of thinking about it is we're going to kind of do a bit of classical reasoning on top of intuitionistic logic. So we are definitely doing intuitionistic logic, we're just kind of doing it in a bit of a classical way. Another way of thinking through it is like this. If you think about what the semantics for intuitionistic logic looks like, the Kripke semantics that we talked about before, it kind of looks a little bit like modal logic semantics, right? We've got some blobs and we've got some arrows between them, and some of them we write P's and Q's and some of them we don't, and that tells us what's true where. Okay, so we know we can do proof trees for modal logic. So if the intuitionistic semantics is basically just modal logic, we should be able to do proof trees for intuitionistic logic on the same basis. And yeah, that's exactly what we're going to do. We're going to write down rules for intuitionistic logic kind of as if it was modal logic. So our rules are going to look very similar to the rules for modal propositional logic. So remember, in modal logic, on a branch, we don't just write down P on its own, we write down a little tag after it, okay? So we say that P is true at world 0 and Q is true at world, 2, let's say, okay? So in general, we're writing down lines like A, N, and also information like N arrow M. When we come to trees for intuitionistic logic, we need a little bit of extra information compared to the trees from classical modal logic. And this is basically because the trees that we've been looking at so far for classical propositional or classical modal logic or whatever, they kind of rely on the law of excluded middle. But that's something that doesn't hold in intuitionistic logic. Okay, so we were trying to work out whether we can get from X to A, and the idea was, well, if A is not going to be true, then not A will be true, and that will close our tree, so then we can infer that A follows from X. So kind of implicitly, as well as using reductio, we're also using the law of excluded middle, but we don't have that in intuitionistic logic. In particular, we can't rely on the assumption that just because not A doesn't show up, A will show up. Okay? We need a bit of extra information. Just like in modal logic, we're going to be writing down lines in a branch like this. Sentence A tagged with a number n. So in modal logic, we thought of those tags as representing possible worlds. Here, they're representing the stages of our investigation. So think about the Kripke semantics. We build it stage by stage, so n would be some stage of that investigation. Now, we're also going to add an extra bit of information. We're either going to put a plus here, or we might put a minus here. Okay, so every time we write down a sentence, we're going to add a tag and either a plus or a minus. The plus is going to mean that sentence A is verified at stage n. And the minus, in this case, will mean that sentence B isn't verified at stage n. Now, we didn't need to do this in the case of modal logic because we would capture the idea that a sentence isn't verified there by writing down its negation. In the case of intuitionistic logic, it's not so straightforward. The sentence B might fail to be verified at stage n, so B isn't verified there, but that's not going to mean that not B is verified there. We haven't got that classical principle of excluded middle, okay? We can't go from it not being verified to not being verified. So we have to capture this information here rather than capturing it with negations here. It's just an extra little complication we have to add in to our notation to capture all the nuances of intuitionistic logic. Okay, so with that in mind, let's have a look at how the rules go. Some of the rules are going to be pretty much just the same as in propositional logic, just with the extra bits of notation added in. So the conjunction rule in propositional logic would go A and B. We would extend the branch and add A and B. The corresponding rule in intuitionistic logic would be the one where we've got that being verified at stage n. So we've got the little plus there. And what we're going to say is if A and B is verified at stage n, then so is A and so is B. Okay, so if a conjunction is verified at some stage of our investigation, then each of the conjuncts on their own is also verified at that same stage. Now that's the rule for a conjunction being verified. What about if a conjunction isn't verified? So now we're looking at the case where we've got A and B, but it's not verified at stage n. So this is going to be a bit like the classical rule for negated conjunctions. So it's going to be a branching rule, okay? If A and B isn't verified, there might be one of two reasons for that. It might be because A isn't verified at stage n, or it might be because B isn't verified at stage n. Or it might be both of those, okay? But at least one of those is going to hold, okay? So either A isn't verified or B isn't verified at that same stage. We don't know which applies, so we branch. So whereas in classical tree tests we had two rules for each connective, one for it on its own and one for it with a negation in front, in intuitionistic trees we're still going to have two rules for each connective. One is going to be the one for it being verified with a plus there, and one is going to be the one for it not being verified where it's got a minus there. Okay, so there's a plus rule and a minus rule for each connective. Okay, so we've seen the and rule. The or rules are very, very similar to the classical case, the modal classical logic case. The rule for closing a branch, it's also going to be similar, but in this case we're going to look at a sentence that is both verified and not verified at the same stage. Okay, that's something we can't have. So if we have A n plus and A n minus in our branch, we can close that branch. Okay, so we're closing a branch, not when we've got a sentence and its negation, but when we've got something that we think is both verified and not verified. That's when we close the branch. Now, it's going to turn out that if you do get a sentence and its negation both verified at the same stage, this will follow, so the branch will close. But there's going to be some cases where we might get this, even though we don't get a sentence and its negation. Okay, so this is the more general rule for closing a branch. So let's use this one. The rules that are a little bit tricky for intuitionistic logic are the rules for negation and the rules for the arrow. These are the connectives that don't behave like they do in classical logic, okay? And or kind of behave classically, whereas negation and the arrow behave in quite a different way. So these are going to have rules that look a little bit more like modal logic rules. Let's have a look at how they go. Okay, so suppose we've got a negation verified at a certain stage, n. We're going to understand this rule by thinking about what it means in a model. And negation in intuitionistic models basically means you never get A. Okay, so you go forward in that model, look at all the stages you get to, you're never going to get an A. So if we get to some stage, there's not going to be an A there. So the if is going to be part of the premise, and the conclusion is going to be you're not going to get A there. So if we can go from n to m, then A won't be verified at m. It's a bit complicated, so let's go through that again. It's a rule with two premises, a little bit like the box rule in modal logic. If not A is verified at n, and m is going to come after n, then A's not going to be verified there. Okay, so at m, A isn't verified. That's what I add to my branch if I've already got those two things in the branch. Let's have a look at the not verified, the minus rule for negation. So this is going to go, if we've got not A and it's not verified at n, why would that be? Well, it would be because at some future stage, A does crop up. So from this on its own, I can infer that there is this future stage M where A is verified. Okay, so what stops not A being verified? Well, A being verified at some future state. So let's just compare those two rules for negation for a sec. If not A starts off being verified, then A ends up not being verified. And over here, if not A isn't verified, then A ends up being verified. So these rules have this kind of Doctor Who-like feature of inverting the polarities. When we start off with a plus, we end up with a minus. And when we start off with a minus, we end up with a plus. So that's one way in which you can help remember what the rules look like. The other difference between these two is that one's a bit like a box rule in that it has two premises and one conclusion, and this one's a bit like a diamond in that it has one premise and two conclusions. So this one is adding a new world, whereas this one is doing stuff with worlds that we've already got in the branch. Okay, that's how things work for the negation. Let's have a look at the rules for the arrow. Okay, so if we've got a conditional, if A then B verified, what that means, again thinking in terms of models, is at every future stage of that investigation, either we don't have A verified or we do have B verified. Okay, so if A's verified, B's verified. So a different way of saying that would be, if we've got some future stage of our investigation, either A isn't verified there or B is. And we know how to pack that if then and either or into a rule. The if bit is going to be another premise. It's going to be that we have this future stage M, and the either or bit is going to be branching. So either A isn't verified at the new world M, or B is verified at that other world M. Okay, let's run through that again. So we're saying, given that we've got a conditional being verified at N, and also we've got this future world, this future stage of the investigation M, then we can infer either A isn't verified there or B is. So here, again, it's like a box rule in modal logic, two premises, and we're going to extend the tree, but this time by branching. The not verified, the minus rule for the conditional, on the other hand, goes like this. If the conditional, if A then B, isn't verified, That must be because we've got a future stage of the investigation where A's verified and B isn't. So we can add all of that information to our branch. So from that one premise, we can add the information that there is this future stage of the investigation, M, where A is verified, but B isn't verified. So again, this rule is like the rule for diamond in modal logic, and that means that the M here has to be a new tag, a new number to that branch. We're not making this inference about some specific stage that we know about. It's just saying there is some stage of this investigation, and we simulate that by introducing a new number here. So M is new to the branch. Okay, so there we've got all of the connective rules for intuitionistic logic. And yeah, they do get a bit complex. Either you just memorize them and get used to using them, or if you're like me and you basically can't remember anything, you think about why they are the way they are by thinking about what the Kripke models look like. Okay, now on top of those rules, there are a few additional rules that we need to get the full whack of intuitionistic logic. And these are basically going to capture special features of the semantics that we're using. Okay, so that those features are, the semantics is basically like modal logic KT4. In other words, it's reflexive and it's transitive. So we're going to add those rules, the T rule and the for rule, to our intuitionistic tree test. Okay, so here we've got a version of the reflexivity rule, the T rule. I've put a plus minus there because it doesn't matter whether it's a plus or a minus. Basically, we're saying if you've got tag N in your branch at all, then you can add the line N goes to N. Okay, and here we're saying if you can go from N to M and M to L, then you can add a line straight from N to L. So transitivity, basically. The final rule we need to add is one that simulates the hereditary principle in the semantics. So this is the idea that if we're going forward in this investigation and at this stage we've got some information, we don't forget that information. We don't lose information that we've already got. So we're always adding. So we're going to say if we've got some primitive sentence P and it's verified N, and also we know that we can go from N to M, then we can add that P is also verified at M. So as I've written this rule down here, it only applies to primitive sentences P, and I think here's the really important bit, it only applies to the verified version of the rule. There's no version of this rule that corresponds to the minus there, sentences not being verified, and that's because just because something isn't verified right now doesn't mean it's not going to be not verified in the future, because we learn stuff. As we go forward in this investigation, we learn new stuff. The idea of this rule is we don't forget stuff. Okay, so primitive sentences, if we know them and we have some future stage, then they're also verified at that future stage. So here are all the rules for intuitionistic logic. Yeah, like I said, they do get kind of complicated. Let me just walk you through how we use them. If we've got some premises, let's say A and B, and we're trying to work out whether conclusion C follows in intuitionistic logic, what are we going to do? So we're going to write down the premises at 0, and we're going to say that they're verified. And then we're going to write down the conclusion, also at 0, and say that it's not verified. Okay, so in this case, we're not going to write down the premises and the negation of the conclusion. We're going to write down premises, verified, and conclusion, not verified. And the idea is we're kind of trying to find a model that makes the premises true or verified, but doesn't verify the conclusion. Okay, remember that that's not the same thing as verifying the negation of that sentence. So we don't want to treat not verifying the conclusion as verifying the negation of the conclusion. Okay, so we're not going to write down not C here. We're going to say C isn't verified. Then we apply the rules, and if we get that branch to close, if we get that tree to close, then we've got a proof. We've proved that conclusion from those premises in intuitionistic logic. If we get a branch that doesn't close, that finishes open, then we've got a counter model. Okay, that inference doesn't hold, and we can build a counter model that verifies the premises and it doesn't verify the conclusion, and we would build that counter model just like we would do it in modal logic. Okay, so using a proof tree from modal logic. So I put a link to that up here somewhere. If you don't know how to do that, go and look at that video. It's exactly the same process. Okay guys, so that's it for today. There we have proof trees for intuitionistic logic. Yeah, they do get a bit complicated, but they're really useful to be able to do for building models, for testing entailment, so it's well worth learning this system. Okay, I hope you've enjoyed this video. Thank you so much for watching this far. I really appreciate it. If you've got any questions, leave me a comment below, and I hope to see you guys back here next time.